Welcome back to the deep dive. Today we are tackling a problem that sounds, well, it sounds like a distinct lack of common sense, but it's actually one of the hardest challenges in the entire field of bioengineering. I want you to imagine trying to stick a Band-Aid on a water balloon.
Okay, I'm picturing it. Not easy.
Now imagine that balloon is wet, it's slimy, it's pulsing, expanding, and contracting every few seconds, and it's not even round, it's lumpy, shaped like a kidney bean or a weird oval. If you manage to get that sticker on there and it wrinkles even a tiny bit, or if a corner lifts up and creates an air gap, the whole medical treatment fails.
And you have just described the absolute nightmare of treating internal organs.
Exactly. We have these incredible drugs, gene therapies, CRISPR, you name it, but physically getting them into a living, moving organ like a kidney or an ovary is shockingly difficult.
It's the classic interface problem. You have this brilliant high-tech software, the drug, but the hardware, the delivery system, is still kind of stuck in the past. If the device doesn't hug the organ perfectly, you get gaps.
And in bioelectronics, air is the enemy.
The absolute enemy.
So today we are unpacking a paper from Cell, published just this month, February 2026, that claims to have solved this using a mix of, well, high-level physics and ancient Japanese art. The paper is titled An Organ-Conformal Kirigami-Structured Bioelectronic Patch for Precise Intracellular Delivery.
Which is a mouthful, so thankfully they gave us a great acronym, the POCKET patch.
POCKET. That stands for Patch for Organ-Conformal Kirigami-Structured Electro-Transfection. Our mission today is to take this thing apart layer by layer. We're going to talk about universal conformality theory, we're going to look at how to zap cells without cooking them, and we're going to see how this device can potentially cure ovarian issues without genetically modifying the eggs.
You know, that last part is the real sci-fi moment for me. It's a strategy they call the relay, and it fundamentally changes the rules of gene therapy.
Okay, let's start with the physical problem first, the wrapping paper dilemma, as they call it. The authors introduced something called the universal conformality theory. Why do we even need a theory for wrapping something?
Well, think about wrapping a basketball with a sheet of standard printer paper. You literally cannot do it without crinkling the paper or tearing it.
Right, because the paper is flat and the ball has what mathematicians call Gaussian curvature.
Exactly. A sphere curves in two directions at once. A flat sheet only wants to curve in one direction, like if you roll it into a cylinder. When you force that flat sheet onto the sphere, you get stress. That stress releases itself as wrinkles, or even worse, blisters.
Blisters sound bad.
In this context, a blister is a gap. The patch just buckles and lifts away from the tissue.
Right.
And if the patch isn't touching the organ, the electricity can't flow, the drug stays stuck in the patch, the therapy completely fails.
So the solution is kirigami. Most people know origami, which is folding. Kirigami is cutting.
Exactly. By making these really strategic cuts in a rigid material, you can turn it into a stretchable mesh. But here's the nuance. You can't just make any cuts. These researchers didn't just hack away at it. They used a very specific pattern called tessellated rotating squares.
Okay, help us visualize that.
Imagine a bathroom floor covered in square tiles. But instead of grout holding them together, imagine tiny little hinges at the very corners of each tile. If you pull on that sheet of tiles, they don't just move apart, they actually rotate.
They spin a little bit.
They spin, and that rotation opens up space, allowing the whole sheet to expand and wrap around a complex curve, like a lumpy ovary, without buckling at all.
But wait, I have to play devil's advocate here. Why go through all this trouble with cutting tiles? Why not just use a stretchy material, like a rubber band or a soft silicone sheet? Wouldn't that just conform naturally?
That's the intuitive thought, right? But here's the trap. Most stretchy materials, like rubber, aren't conductive. And if you try to put electronic wires on a rubber band, when you stretch it, the wires break. Or their electrical resistance goes haywire because they get thinner.
Ah, so you need the material to act stretchy, but the actual electronics need to stay rigid and stable.
Precisely. Kirigami lets you use these high-performance, rigid materials that behave like a fluid. But there is a catch. You can't just guess the size of the cuts.
And this is where the math comes in. The universal conformality theory.
Right. They derived a formula to find the Goldilocks zone. They take a 3D ultrasound of the specific organ, say your left kidney. From that, they calculate its curvature, which is denoted as K.
Okay, so we have the shape of the target.
Then they input the material properties of the patch, the stiffness, or Young's modulus, which is E, the Poisson's ratio, V, and of course the thickness, T.
So you feed the organ shape and the plastic stiffness into the algorithm.
And the algorithm spits out the perfect design. It tells you exactly how big the tiles need to be, that's the unit cell length, L, and exactly how wide the hinges need to be, the hinge width, S.
Why does the hinge width matter so much?
Well, think about it. If the hinge S is too wide, the sheet is too stiff, it won't wrap, it just acts like a board. But if the hinge is too narrow, the slits open up these huge gaps. And remember, we need to deliver drugs. If you have giant holes in your patch, you have giant areas of the organ getting zero treatment.
So they are optimizing for coverage.
Yes, they call it the effective coverage ratio, or FIF. They proved mathematically that they can hit 95% coverage on any organ shape just by tuning those two variables, L and S.
That is wild. They basically solved the wrapping paper problem with an equation.
It creates a fit so perfect that it eliminates those blisters we talked about. No gaps.
Okay, we're about 5 minutes in, so let's pause for our first recap. Let's really anchor what we've learned.
Sure. First, the problem. Rigid electronics don't stick to wet, curved organs. They buckle and lose contact. Second, the solution, kirigami. Specifically, a pattern of rotating squares that allows the material to expand and conform. And third, the innovation. They didn't just guess the pattern, they derived a universal conformality theory. By measuring the organ's curvature and the material's stiffness, they can calculate the exact hinge width and tile size needed to ensure 95% of the patch touches the organ.
And here's a question for you, the listener. I want you to think about wrapping that basketball again. If you could cut the paper in a specific way so it hugs the ball like a net, you've solved the geometry problem. But solving the geometry is only step one. Now we have to deliver the payload.
Right. A nice shape doesn't cure cancer.
Let's look at the pocket device itself. What is this thing actually made of? The paper describes it as a 4-layer sandwich.
And this sandwich is incredibly thin, about 114 micrometers total. That is barely thicker than a human hair. Let's build it from the bottom up, starting with the layer that actually touches the organ.
Okay, layer 1, the nanopore film.
This is a PE film, your standard medical plastic, but it's only 12.5 micrometers thick. The key feature, though, is that it is riddled with tiny holes, or nanopores, that are about 800 nanometers in diameter. This is the critical interface.
Okay, moving up.
Layer 2.
This is the hydrogel layer, specifically polyacrylamide or PAM. This is the storage tank. It's loaded with the payload, which could be DNA plasmids or, other drug molecules.
Layer 3. The electrode. It's a network of silver nanowires, or EGNW. This is highly conductive, but also really flexible, so it doesn't break when the kirigami stretches.
And layer 4, the top bun.
That's PDMS. It's a silicone-based polymer. It basically acts as insulation and encapsulation to protect the whole device.
So we have plastic with holes, jelly with drugs, silver wires, and silicone on top.
Yeah.
How do they power this thing? I assume there's no battery inside the patient.
No battery. It uses a wireless powering module. There's a receiver coil implanted just under the skin that harvests radio frequency, or RF, energy inductive coupling, from an external transmitter. It converts that energy into a square wave voltage, typically running at about 20 volts.
20 volts? That sounds like a lot to put on a sensitive organ like an ovary. Wouldn't that just, fry the tissue?
This brings us to the nanopore mechanism, which is arguably the most brilliant part of this entire design. Remember that bottom layer of PE plastic? It is an electrical insulator.
Meaning electricity can't go through it.
Exactly. The only path for the current to flow is through those tiny 800 nanometer holes.
Oh, it's like putting your thumb over the end of a garden hose.
Perfect analogy. You have the same amount of water, or current, but you are forcing it through a tiny opening. This massively increases the pressure, or the voltage, right at that specific spot. It creates a really focused electric field.
So even though the overall voltage is 20 V, the effect at the hole is much, much more intense.
Yes, but only at the hole. This creates what they call a transmembrane potential, or TMP, of greater than 1 volt on the cell membrane, sitting right under that pore. And that 1 volt is the magic number to punch temporary holes in the cell, a process called electroporation.
So it punches a hole in the cell. But how does the drug get in?
That is the second effect, electrophoresis. The electric field physically pushes the charged drug molecules out of the hydrogel through the nanopore and basically shoots them into the cell. The paper says this accelerates transport by 1,000 times. 1,000 times faster than just passive diffusion.
And because the resistance is highest at that tiny pore, that's where any heat is generated.
Correct. So the heat gets generated in the fluid within the pore, not in the broad tissue. They measured the temperature rise, and it was negligible, less than 0.02 degrees Celsius. So no cooking the organ.
Safe, effective, and fast. Okay, let's see this in action. The paper has two massive case studies. The first one is about ovaries and gene therapy.
This is fascinating. They looked at mice with a BRCA1 mutation. In humans, BRCA1 mutations significantly increase the risk of ovarian and breast cancer. They also cause DNA damage to accumulate, which leads to infertility.
The problem with treating ovaries, though, is the eggs. We have this huge ethical line we do not want to cross, germline editing. If we fix the mother's ovary but accidentally edit the DNA of the eggs, those changes get passed down to her children. We want to cure the patient, not design the baby.
Exactly. This is the spatial control challenge. And Pocket solves it using what they call the relay strategy.
Like a relay race. Walk us through this.
So because of that nanopore mechanism we just discussed and the controlled 20 volts, the Pocket device only transfects the surface epithelial cells. These are basically the skin cells of the ovary. The electric field literally does not penetrate deep enough to hit the eggs, or oocytes, which are buried deep inside.
So step one. The patch zaps the surface cells and gives them the BRCA1 plasmid, healthy DNA.
Right. Those surface cells take the plasmid and start producing the healthy BRCA1 protein. But here's the aha moment. Those surface cells also produce mRNA from that plasmid. Then they package that mRNA into what are called extracellular vesicles, or EVs.
EVs are like nature's FedEx trucks.
They are. They really are. And these EVs naturally travel deep into the interior of the ovary. They carry the healthy mRNA to the inner cells. The inner cells absorb the EVs and then use that mRNA to repair their DNA damage.
So the surface cells act as a factory and the EVs act as the delivery drivers to the deep tissue.
Precisely. And because mRNA is transient, it degrades after a while, it doesn't permanently alter the genome of the eggs. They confirmed this with whole exome sequencing on the offspring. No foreign DNA entered the next generation.
That is huge. They treated the organ without touching the germline. Did it work?
It worked spectacularly. In the mutant mice, DNA damage markers, specifically H2AX, were significantly reduced. Hormone levels like estrogen and progesterone went back to normal. And most importantly, fertility was restored. The treated mice had normal litter sizes.
Wow. Okay, we are at the 10-minute mark. Let's hit checkpoint 2.
Let's summarize the device in this ovary application. First, the device. It's a 4-layer stack. Nanopores on the bottom, then hydrogel, silver nanowires, and PDMS on top. Second, the mechanism. The nanopores concentrate electricity to inject drugs via electroporation, but without heating the tissue. And third, the relay strategy. In the ovary, the patch only touches the surface. It turns surface cells into factories that send safe, mRNA-loaded FedEx trucks, the EVs, deep inside to fix the organ without genetically modifying the eggs.
And a question for you to ponder. Why is that relay strategy so important? It effectively solves one of the biggest ethical dilemmas in gene therapy. You can treat the organ of a potential mother without worrying about genetically modifying her future children. That opens up doors that were previously welded shut.
It really does. Now let's move to the second case study, the kidney.
This one is less about gene therapy and more about repair and long-term durability. They looked at something called ischemia-reperfusion injury, or IRI.
Right. This happens during kidney transplants. When you take a kidney out, it loses blood flow. When you sew it into the new patient and the blood rushes back in, it causes this massive inflammation and tissue damage, which can lead to scarring.
And usually doctors give the patient oral drugs, like dexamethasone, to fight that inflammation.
They do, but they have to use really high doses. And steroids like dexamethasone have terrible systemic side effects, bone loss, increased risk of infection, immune suppression. It's a real problem.
So the Pocket team said, why not just put the drug directly on the kidney?
Exactly. Localized delivery. They implanted the Pocket patch on mouse and pig kidneys for a full month, 30 days.
Wait, they left it inside for a month. Usually, if you leave a piece of electronics inside a body, the body fights back. You get fibrosis scar tissue that walls off the device.
That is the standard reaction, but remember the universal conformality theory. Because the kirigami structure fits the kidney so perfectly and it moves with the kidney as it expands and contracts, it doesn't rub, it doesn't irritate the tissue.
So the body barely notices it's there.
Correct. They found that the fibrous capsule that did form was incredibly thin and loose. It didn't block the drug delivery at all.
And how did they handle the dosing? You can't just dump a month's worth of steroids on an organ all at once.
Right. They modified the hydrogel to hold enough dexamethasone for 30 days. Then they used an electro-triggered release. Every day, they send a wireless pulse that releases about 1 microgram of the drug.
It's an implantable pharmacy.
An on-demand implantable pharmacy. The results were stark. The kidneys had significantly less scarring and tubule damage compared to the mice getting oral pills, but the real win was the side effects.
Or the lack of them.
Exactly. The mice with the pocket patch had normal bone density and a normal immune system. The mice taking the pills had significant bone loss. Plus, the drug exposure in the kidney itself was 2.4 times higher with the patch.
So more drug where you want it and basically zero drug where you don't.
Sure.
And they proved this can scale up.
They did. They implanted these patches in pigs using laparoscopic surgery, minimally invasive keyhole surgery. The patch could be rolled up, inserted through a tiny tube, and then unrolled onto the kidney.
That is the step toward actual clinical use.
Yeah.
If you can do it laparoscopically in a pig, you are on the road to doing it in a human.
And just to summarize the sheer amount of evidence here, they didn't just do one test. They used finite element analysis, or FEA, to prove the physics. They tested on harvested pig and human ovaries ex vivo. They did the mouse models for BRCA1 and kidney injury. And then they did the large animal pig models for durability.
A very, very complete package. Let's do our final checkpoint, number 3, before we wrap this up.
Right. First, the kidney application, a 30-day implantable pharmacy. Second, the benefit. Localized delivery avoids systemic nightmares like bone loss. Third, the durability. The kirigami structure works because it moves with the organ. If it doesn't fight the organ doesn't fight back with scar tissue. And finally, the versatility. It works on tiny mouse organs and large pig organs.
And the question for the listener here is, consider the shift from taking a pill that goes everywhere in your body, your brain, your bones, your blood, to wearing a smart patch inside your body that treats only the sick organ. How does that change the way we think about medicine? It's no longer just chemistry, it's geography.
That is a profound way to put it. It's precision medicine, but spatial precision.
So we've unpacked the pocket patch. We've got kirigami physics, nanopore mechanics, the ovarian relay, and the kidney pharmacy.
Yeah.
What's the final synthesis here? What's the big takeaway?
For me, this paper really represents the solution to the interface problem. We have spent decades developing these amazing drugs and gene editors, but we have struggled to get them across that last millimeter from the needle, to the cell. Pocket solves that interface. It ensures contact via kirigami, and it ensures entry via nanopores.
It doesn't matter how good the drug is if you can't get it inside the door.
Exactly. And looking forward, the authors mentioned something really provocative in their discussion. The current device uses PET and PDMS standard medical plastics, but they suggest future versions could be made of biodegradable materials like PLGA or magnesium.
Oh, wow. So imagine a patch you implant during a surgery to heal an organ.
And once the job is done, it just dissolves. No second surgery to remove it, nothing left behind.
That is the sci-fi future I signed up for.
And one final thought to leave you with. Visualize that relay mechanism again. We often think of medicine as conquering the body, forcing a change. But the relay works with the body's natural logistics. It uses the cells to make the EVs to carry the cure. It's a partnership between the electronic and the biological.
Working with biology, not against it. That's a great place to leave it. Thank you for listening to this deep dive into the pocket patch.
It was a pleasure.
See you in the next deep dive.